Welcome everyone to the ilifu online training workshop. Today we're going to go through an introduction to the ilifu research facility. So this is more basic training topics, and then in 2 weeks time we're hosting another workshop which will cover further introductory topics as well as more advanced topics. I just want to introduce myself and the support team that are here today. So I'm Jeremy. I'm the operations manager, and I also provide support for the ilifu research facility. Jordan is here as well, who's the astronomy support personnel. Jordan, you want to introduce yourself? Or?
Yeah, I can again later when I present, but this is me.
Sure. And then Dane Kennedy is the support person for bioinformatics. If you want to say hi, Dane.
Hello, this is me.
All right. So just for everyone's information, that the workshop is going to be, or is currently being recorded. So we record the videos and we make the videos available from the ilifu website. There'll be a link in the presentation. So you can reference the recording at a later stage, or you can share the recording with any project members that it might be relevant to. And the presentations will also be available with the recordings. And then we're going to go through presentations and then provide a demo. And then Jordan's going to talk about a number of subjects and provide a demo. And then we're going to have a Q&A session at the end of the workshop. So there's quite a lot of information to go through. So we're going to go through all the topics and information, and then at the end of the session, we can have a Q&A period where you're welcome to ask us any questions here in person. Just get onto the right screen. Okay, so in terms of the topics that we're going to cover, I'm going to go through the support channel that are available and the resources that are available. I'm going to talk about just the basic services or introduction to the facility. I'm going to go through the directory structure on the ilifu facility, talk about the different software environments available, and then provide a demo on using the terminal and also using JupyterHub. Jordan is then going to provide an introduction to the SLURM cluster and do a demo on submitting jobs and interactive sessions on the SLURM cluster. And then he'll also touch on the best practices as well. So I'd like to start by pointing out the support channels where you can find information about the ilifu services and other resources. You can email the support team at support@ilifu.ac.za. So we have a ticketing system and a team of support personnel who will respond to any questions or issues that you might have. Our user documentation for the ilifu facility is available at docs.ilifu.ac.za. So I'll just show an example of the website. So through the web browser, it basically provides a step-by-step guide from how to apply for an account on the ilifu facility. Any issues that you might have with SSH keys, if you need to regenerate keys, or what to do if you've lost your SSH key for access. It talks about accessing the different services, changing your password. A lot of the information that we're providing in this introductory session is also directly available in the user documentation, specifically in the getting started section. There's also some of these topics are expanded in greater detail. For example, the software environment and how to submit jobs on SLURM are expanded on in the technical documentation. And there's also domain-specific documentation for astronomy related software, as well as data transfers from the Soraya archive. And then there's also domain-specific information about bioinformatics specific to CBio and software used by this project group. We also then have a ilifu status page So this provides information about the current state of ilifu services. So this is at status.ilifu.ac.za. I've got an example of it here. So at the top, it'll give a brief overview of the current state of the system, and then it will give indication of the status of different services, and you can drill down and look at different issues that might exist. So this is one of the resources. If you are experiencing an issue, you're welcome to come and look at the status page, and then if it hasn't been picked up, send a support ticket to the support email. And then, as mentioned, we have the training videos. So we have last year's training videos available on our ilifu website. This is the link here. And then once the training videos for this year are completed, we'll upload those videos along with the presentation slides. So in terms of the ilifu Research Facility, the facility supports a variety of different projects, particularly within the fields of astronomy and bioinformatics. And these projects have various requirements. In order to support the different projects, we offer both data management in the form of storage and data transfer services, as well as a flexible compute environment. In order to achieve this flexibility, we provide a number of different services. The primary compute service is the SLURM cluster. And so this is a job scheduler. This service allows for a pool of compute resources in the SLURM cluster to be available to users. Users submit their jobs, whether it's a small script, a workflow, or an extended pipeline, to the SLURM scheduler. The jobs are then placed in a queue and are initiated as soon as the requested resources become available. Users are also able to use the compute resources in the cluster in an interactive way, requesting a session on a compute node, and then you're able to interact with software via command line or through X11 GUI interface. And Jordan will go through the SLURM service in greater detail later in the presentation. So the other services that we offer is there's JupyterHub, which is a Jupyter Notebook web interface. This is for primarily for development. And then for software on the cluster, we provide software through Singularity containers and through modules. And then we offer other services such as data transfer, including Globus and Carter, which is an astronomy visualization tool. So we host a Carter server. Probably talk about more in the second advanced workshop in April on that topic. So in general, users will interact with the cluster in two ways. So when you sign up, you'll get a username and provide us with an SSH key, and you'll get a username and password. So the way that you interact with the facility is either through the shell terminal. So you log into the SLURM login node or one of the other services via the terminal through SSH. So an example is on the bottom of the slide, SSH and then your username at slurm.ilifu.ac.za. So this will take you onto the login node. Then another way to interact with the services is through a web browser. So you can access the Jupyter service through jupyter.ilifu.ac.za. So in order to navigate the storage and different directory spaces in the cluster, I just wanted to go through the directory structure and what's available. So there are a number of common areas, such as a user's home directory. So every user has a home directory. And then other common areas is the Scratch storage. So there's two Scratch spaces at the moment. There's Scratch users and Scratch 3 users. And we also have a common software area where we have common modules, Python, and other containers, and then also some bioinformatics and astronomy containers exist at software as well. The rest of the directory structure is broken down into groups. So on the cluster, we have astronomy and bioinformatics. So we have members who are part of the IDIA group, or CBio, which is the UCT computational biology group. Otherwise, there's also the DERISA project, which members are registered under an ilifu group. And then there's a separate directory structure for those projects. Just in terms of the common areas, I just want to backtrack. So one of the key points with your home directory @/users is that this directory is where you land on the SLURM login node, but this directory is also, the mount is only 40 terabytes. And so this is shared amongst all users on the cluster. And therefore we request that users don't put large data or large files in their home directory. So the home directory is only used for scripts, small notes, and maybe documentation, that sort of thing. And then the Scratch and user space. So the Scratch space is specifically used for data processing and specifically only used during data processing. So what this means that the usage of the Scratch spaces is supposed to be temporary, and that you run workflows and produce output on the Scratch space, but once you've finished data processing, you remove all data, whether it's intermediate products or final products, is either deleted or moved to longer term storage locations. So then for the directory structure broken up into the different project groups. So for IDIA, each IDIA user will have a private workspace at /IDIA/users. So this is where you can store data products a little bit longer, or there's also a project space at IDIA project. So any data that you're not ready to share with your project can be placed in your personal workspace. And this is limited to 10 terabytes per user. And then every project will have a dedicated project workspace. So these project workspaces are shared amongst all users within a particular project. And so you can use these directories for sharing data, for sharing output, custom software containers can be shared here. And for IDIA specifically, raw data from the Meerkat Observatory will be available from the project directory. The other directories under IDIA are software and the software containers. And so those are mostly, well, they're basically all astronomy specific containers. The other groups share a similar structure. For CBio group, users will have a personal workspace. The project folders exist for individual projects, and there's software. And similarly for the ilifu directory structure. I just wanted to reiterate in terms of the workflow and the use of the different directory structure. So just to reiterate that the home directory at /users is small and for small scripts and small files only. And then generally for the different groups, so N here represents IDIA, CBio, or ilifu, and then the project's user and data. So this is more longer term storage. So you'll have project data existing in these locations. So a general workflow is that you run the processes on the facility or your jobs, and they run on Scratch 3 or write output results and intermediate files onto Scratch 3. So they're reading the data from the project folders and writing output or running processes, specifically writing output onto Scratch or Scratch 3. Then these would produce results in intermediate files, and then you would selectively write only what you need to keep back into a longer term storage, which is, again, in either projects or users, depending on your use case. And I just pointed out that generally the data directories that are provided in the different groups are usually read-only. So you tend not to write into those directories, but that's just the basic workflow for the directory structure or the purpose of the directories. Okay. So I just wanted to talk about the software environments on the ilifu. One of the ways in which we provide a software environment is through Singularity containers. So these are similar to Docker containers, but they provide increased security, which is why they're used for science cases on HPC type environment in a cluster. So these containers allow for an encapsulated software environment that is separated from the underlying operating system. container may have a single purpose, have one software, or it could have a suite of software packages that is used for a particular workflow. And a container will include all the binaries, the libraries, the environmental variable set for that specific workflow or pipeline. And these containers are then made available on our storage, and they're made available to all the virtual machines and services. And so you're able to access the software from anywhere on the research facility. And the other benefit of containers is that if you have a particular workflow or container structure for your work group, these workflows can be shared amongst your project members. We offer support of existing containers. So a lot of these containers are astronomy based. So for example, CASA software is for radio astronomy, data reduction to produce radio images. But we also provide bioinformatics containers as well, Python and R and other software. So we generally maintain and support a range of containers. But if we do not offer the software that you require for your project, please do contact us at support, and we will help. We'll put together a container for you for your use in the cluster. In addition, you are able to build your own containers, not on the cluster itself, but you can migrate containers from other locations to the cluster and utilize them. And we'll probably discuss this expand on this topic in the advanced topic in April, in the advanced workshop. In terms of using containers, it's a pretty simple process. So you can interact with the container in a number of different ways, one of which is interactively. So you can shell into the container. So you would interact with the container in a command line interface way. And so to do this, you would run the command Singularity shell and then the path to the container. That would place you inside the container on the command line, and you can interact with software that exists inside the container. So as an example, for the Astro Pi 3 container, which is quite frequently used for astronomy software, this is a monolithic, a large container with a large amount of different astronomy software. An example command would be Singularity shell and then a path to that specific container. And then you could run Python or run a script with software inside that container. Alternatively, you can interact with a container in a non-interactive way. So you can just, and this is how you would submit a job using a container with SLURM. So you would run a command using the exact parameters. So Singularity exec, the path to container, you choose the software that you want to use that exists inside the container, and then any parameters or input parameters or scripts that you want to apply. So an example here would be Singularity exec, and then the path to, for example, the CASA container that exists on the facility, and calling the CASA software, you're passing the parameter to pass in a script, which is the myscript.py. Another software environment, or another way that we provide software environment, is through modules. So modules allow users to dynamically change their environment. Modules themselves either change a user's path to point to specific software, or they provide an alias, which is usually a shorthand command to run software. So you can view the modules that are available on the ilifu facility currently by running the command module avail from the terminal. So this is just an example output. You'll see something similar to what's on the slide. The modules are broken up into modules that are common to all users. So for example, a lot of the coding languages, and then there are specific modules for astronomy and bioinformatics. I just want to point out that when selecting a module, if you don't indicate the version number, it will load the module that is the latest version. For example, if you load module load R, you'll get R 4.0.3, and this is indicated by the capital D next to the modules, which are the default modules. If you want a specific version number, you would enter that as part of the module name when loading the module. So you can look at information associated with modules using the module help and then the module name. The help information may also indicate if there's a specific alias available when the module is invoked and how that alias would be used. A module can be loaded using the module load and then the module name command. And currently loaded modules can be removed using the module purge command. And for additional options about the module software, you can view package information with the module -- help from the command line, which will provide additional parameters. And just to note that you are able to load multiple modules at the same time. Finally, I'm just going to talk about JupyterHub. So we provide this as a service. It's mostly used as a development environment, and it's accessed through a web browser at jupyter.ilifu.ac.za. And I'll provide a quick demo of using this service. Okay. So I have JupyterHub open here in a web browser. So just a reminder, the two ways to access this ilifu services are either through password or through SSH. So you'll be provided with a password when you sign up. We do recommend users to please change their password the first time that they log in. So in this instance, from the web browser, from jupyter.ilifu.ac.za, username and password, sign in. Credentials. So at this point, you'll be provided with a screen about available resources. So when you're launching a job in Jupyter, you're actually using the cluster resources. So they're compute nodes that are dedicated specifically for Jupyter. So you can select a size of the node depending on your work. Obviously, you tie up the resources. So we prefer, or we would request users to only use the resources they need at the time of for their job development. So I'm just going to go with the minimum, which is one CPU, 7 gigs of RAM. And obviously, so the maximum here is 32 core and 232 gigs RAM. So that's a full compute node. And there's split different number of resources in between. So you would select your resources. Just in terms of what's available, the node's free. This suggests that the 73 of the current available resources, 73 minimum nodes could be spun up and etc. 2 max nodes are available, etc. So I click start to start a session. At the moment, Jupyter is majority, well, we provide software coding in Python and R, but there are other languages available. We just haven't necessarily had the request for it, but we can provide additional kernels for different languages. So I'm just going to close this notebook. So this will be the dashboard where you land. These are different kernels that are available within the service. Majority of the different kernels are astronomy, but there are a couple of specific, well, like common ones such as R, Python, Python 2, and Python 3. So this kernel AstroPy 3 is a very common astronomy one. So this is actually a container behind the kernel, which has a large amount of Python astronomy packages available. So you would just click on the kernel that you would like, and then this is a Python development environment, and you could code from this point and run code. You can switch the kernel to an alternative kernel from the kernel menu on the side. You can select a different kernel here. And then I just wanted to, I guess, I've got an example notebook. So here the code hasn't run, but you can run the code with the play button, or there's a lot of different keyboard shortcuts. So running basic Python code, outputting plots, you can print variables. So this is all just basic Python usage. Useful addition to Jupyter Notebooks is that you can view different functions of a particular package using a question mark. So here I'm looking at the function annotate of matplotlib, and this will provide the documentation or the doc string associated with that plot inside the actual development environment, which is very useful. And then you can also run commands to the underlying terminal using a magic command, which is the exclamation mark. So you can look at the current present work directory. So here I'm sitting in my home directory. The directory structure is visible folders on the side on the left. Another useful command that I just wanted to introduce was pip freeze, indicates all the Python packages installed via pip. So if you're running exclamation and pip freeze, you can see all the Python packages that are available inside this kernel. Most of these are astronomy specific. So I think, I guess one of the other important aspects of Jupyter Notebook is to close down your notebook when you are no longer using the resources. So because the request that we did in the beginning, where you launch a session, that's actually utilizing resources on the cluster. So once you've completed your development session, you can go File and Hub Control Panel, and you can stop your job. So stop my server, and this will release the resources that you've claimed. Sure. I've just got a question. You can ask the question now. I just can't see the. How do I see the participants?
Can I suggest we take them at the end, since that's the allocated time we have, and we're a bit pushed to get through the rest?
Sure. Yeah, absolutely.
Or you can type it in the chat if you are worried about forgetting it, and we'll come to it at the end.
Thanks, that's probably best. All right, and then starting my server over here will take you back to the session resource request page. And I think that's all I wanted to show for Jupyter. The other way to interact with the cluster is through the terminal. So here I'm going to SSH in to the SLURM login node. All the VMs, the services, are based on Ubuntu 18. So any of the Ubuntu command line functions will work here. So you can see when you log in, the work directory is your home directory of /users. You can view the contents of your directory with the list command. I just wanted to show the different, so for example, the IDIA projects, this is all the different astronomy projects that currently exist. And similarly, I don't think I have access to permission tonight for ZBio, but for example, the ilifu projects, the bio are available from here. Sorry. Then there's also, each user will have a personal space on Scratch. So I have a Scratch Jeremy. Sorry, what have I done? Just and similarly, another Scratch workspace is Scratch 3, which is available to use as well. And I guess one other point is the list of available containers. So we do have the containers listed, or the supported ones, on our user documentation, but just as information for the IDIA software with astronomy containers are available here. You can view what's available. So the astronomy AstroPy, so this is the kernel that we were using in Jupyter. Other software, Simba, Sophia, the Kaza software is available. So they're either listed by the version numbers or by the latest date. And then each container will have a symlink that points to the latest stable version. So for Casa 5, this is Casa in Python 2.7 is will be we haven't updated that one, but yeah. So that's an example of the software environment. And then one other key point is once you've logged into the login node or any terminal environment to please change your original password that was provided. And you can do that using password command like so. And I think that's everything that I wanted to cover. So I'm going to hand over to Jordan.
Thanks, Jeremy. Cool. So I'm just going to share my screen here. Can you see that all good?
Yeah, I can see the presentation.
Cool. Yeah, so as Jeremy said at the start, I'm Jordan Collier. I'm the ilifu support astronomer at IDIA, and together with a growing team of astronomy support, we're going to be the main point of contact for the astronomy users on the ilifu system. And I'm going to be mainly talking about SLURM and the cluster, and SLURM being the job management software that we use. I just want to introduce the current era of big data first. So perhaps some of you have been doing research long enough that you remember when for any data set, whatever field you're in, you could download your data to your laptop, you could process it there, visualize it there, and then publish a paper about it there. But the problem is these days for big data, often the specifications of your laptop or maybe even your desktop aren't very good. You want more storage, more memory, more CPUs, and perhaps you even want to share your data with other collaborators. So this may lead to getting set up with a server or a VM, a virtual machine, and then multiple users could connect to that via SSH, which Jeremy introduced, secure shell. And you could do heavy processing there. The specifications on that would be a lot better than, say, your laptop, and you could collaborate with your colleagues on the data there. But the problem is that you're sharing the resources and you're limited by the memory, the CPUs, and the storage of that single machine. And so the solution is to combine many of these together. We may refer to these as combining many computers or many machines, many servers, many VMs, virtual machines, maybe even many boxes together. And basically what you want is to be able to have a job management software. So something that manages the resources across all of these machines and is able to schedule jobs so that you're not trying to share the same resources and potentially step on each other's toes, maybe max out the memory and kill someone else's process or something like that. In the later advanced training, we'll talk about how we're able to utilize many machines at once through a single process. But for now, I'm going to talk about our job management and scheduling software, SLURM. So firstly, just to introduce the facility, adding to what Jeremy said, ilifu is a tier 2 data intensive research facility, and it's a joint cloud platform for astronomy and bioinformatics. We have roughly 85 nodes, each with 32 CPUs and generally 256 gigabytes of RAM, and then a few with 512 gigabytes of RAM. And then quite soon we'll have roughly 6 petabytes of usable storage between our two file systems, BGFS and CEFFS. And then for basically any South African research institution, we've got very quick 10 gigabit a second network access. So the first thing I want to talk about is kind of what happens when you log in. So you can read about, in our documentation, you can read about submitting jobs to SLURM from the login node, as well as interactive SLURM sessions with and without X forwarding or X11 support. But what I'm going to talk about is basically when you first log in, you'll land on the login node. And basically, this is to run your SLURM commands and submit jobs from here, but not to run your software or heavy processing. We might also refer to this as the head node, and it's where you run these SLURM commands. It's not where you run your processing. Where you should run your processing is on a compute node. And these are basically when you submit SLURM jobs, this is where they go. We might also refer to these as worker nodes. And generally what you're doing is launching a Singularity container and you're running your processing there. So you can see in this schematic here, we've got the login node, we've got this partition, which is called main. And this is basically just a grouping of compute nodes. There's roughly 80 nodes. Because we're a cloud facility, we're able to kind of expand and minimize this as demand for other projects is brought in. But basically we have these compute nodes where we want to run our processing, and we interact with those via SLURM with a particular partition. And then we have the Jupyter spawner partition as well. And so this is what's going on in the background. And so as Jeremy said, we SSH in, or perhaps we connect to the Jupyter spawner, and then we'll run our job on a particular partition. As I say, the main partition has about 80 nodes. We have a high mem partition, that's the 512 gigabyte nodes. And there's 2 of those. We have 4 GPU nodes, and then currently 12 Jupyter nodes. So some SLURM commands are shown here. You can access the SLURM documentation via this URL, and it has a lot of useful information about syntax and different commands. But what I'll highlight are the ones listed here, which I'll also demonstrate later. So for instance, you've got sinfo, and this shows you the partitions and resources being used or available. We've got SQ, which shows all the jobs in the queue, either that are being run or that are waiting to be allocated resources. You can show your jobs with SQ option your username. You can submit a batch job through sbatch and then the name of the sbatch script you wrote. You can also pull up the help with the help option. You can cancel a job with scancel and then the job ID. And you're given this job ID once you run the sbatch command. It outputs to your screen what the job ID is. Or if you forget it, you can pull up SQ or saccount. Saccount is the last one I'm showing here, and this shows the status of recent jobs that have run or perhaps jobs that are still running. So here's an example sbatch script that I've written. So from the terminal, we could imagine calling cat and then the name, and this displays the contents. So we first got the hashbang, which just means you're running this in bash. Basically, that's almost always going to be the case. We give the job a name. So these are the job description parameters for sbatch. Always has the hash and then sbatch in capitals. So we give it this name, we give it a wall time, which is basically the limit on how long it will run. This I'm just doing for a minute because it's a very simple script. I give it a memory limit of 4 gigabytes, and then I specify where standard error and standard out are going to. So these are 2 streams of outputs that normally just go to your terminal screen. But if you didn't know, there are 2 different streams. One's for any errors in your workflow and one's for the standard output. And so these go to 2 different files that we specify here. And then I also specify my account, which we'll be showing in the advanced workshop, but this is quite important for our kind of reporting infrastructure and understanding the different demand and also accurately capturing the resources run by the different projects. So I can then module load Python, which I'll show later on, but this is kind of following what Jeremy showed. And then I can Python myscript.py. And so this is my contents of the sbatch script, and then I can run that like so, sbatch and then the name of it. Here's a similar example, but in this case, I'm calling a Singularity container to do with this CASA software for radio astronomy that Jeremy mentioned. The software doesn't matter, the syntax would be the same. So here I call Singularity exec, the path to the container, the call for the software, which in this case is CASA option C, meaning you're passing in a script, and then the script name. And then I also submit that with sbatch and then the job name. Now, something we've done recently that I'll show is we've actually added modules for Casa, which point to these containers. So you can actually simplify this call with Casa load, sorry, module load Casa, then the version, and then Casa Pi, option C, your script. So I'll show this a little bit later, but it's a much more simplified version. We can also run an interactive job, which is at the same URL as before, but just a section later down. The way that we do this is with srun pty bash. This just means sudo terminal, and it basically gives you an interactive session on the compute node in the terminal that you're already in. And the default is to have this limited to 3 hours and 7 gigabytes of RAM. But if you have a better estimate on the wall time and memory allocation that you want, then you can pass those in as time, 1 hour, 64 gigabytes, for instance, and then you could even run the Singularity call and software from there. And then, of course, you can pull the help up if you want to see the help. If we want to use a GUI, a graphical user interface with X forwarding, then what we would first need to do is SSH option Y and then your username. This enables X forwarding. And then we would do srun as before, but with this X11 parameter. And again, if we want to specify different arguments to the default, we can do so. We can also even say QoS interactive, which means give me an interactive quality of service. In other words, give me a higher priority to get into the queue more quickly because I'm doing something interactive. Cool, so let me demonstrate some of this. So here's a terminal where I can log into the SLURM.
Jordan, could you increase the size of your terminal?
Yeah, sure. Sorry, I thought I had enough. Is that all right?
Could be a little bigger.
Okay.
I think that's fine.
Okay, so I can SSH jcollier at slurm.ilifu.ac.za, and this will log me in. Just going to clear that. So from here, for instance, I can run sinfo. That's a good one to start with. This will show me the resources being used and available. So for instance, I can see 23 are idle. That means they're completely available. 18 are mixed. Some of the resources are being used. And then 23 are completely allocated. So no resources on those nodes are available. I can run SQ and see what's in the queue, basically the different jobs from the different users. I can run SQ option U my username, or if you like, you can do the user environment variable. I've got nothing in the queue right now, which is good. And then if I want to, for instance, connect to a compute node, I can use the syntax mentioned earlier, srun pty bash. And you'll see that I might just bring this up a little. You can see that the prompt has now changed so that it says I'm on compute 21. So this means I'm now on a compute node, and so it's safe to run my software. So for instance, I could do Singularity shell, IDIA software containers, and I can use this Casa stable container I mentioned before. So this will shell me into the container. Again, the prompt has changed to show me I'm in the container. Then I could, for instance, say which Casa, and it knows now how to find Casa. I won't launch that right now. I'll show it a little bit later. And then I'm just going to log out of that with Control D, or I could type exit. So back to the login node. If I wanted to do something with X forwarding, so for instance, I'll log out again, and this time I'm going to do option Y to enable X forwarding. And so now from here, I can go srun p2y and I can say X11. I could even add the quality of service as quality of service interactive. And then I could even just call Singularity exec from here, and then the path to the container as before. And then I could actually just exec Casa like that. So this is kind of long syntax, hence the modules that we offer, which I'll show in a moment. But this is going to launch Casa now, this radio astronomy software I mentioned. Again, the software doesn't matter, but the syntax. So you can now see this has opened the CASA log, which is with X11. And so that's means my syntax has worked to enable X forwarding. Okay, so I'll just log out again with Control D. And then just to quickly show the other approach, so I can say module avail CASA, and you can see the modules available here. I can also, for instance, for a specific module I may want to know about, say module help, and then that, and this lists a lot of helpful information about how to basically, so we can first do the same syntax, we can copy and paste that, connect to the compute node, we can load this specific module, and then we can run these commands. So we could run CASAPy to launch CASA. I won't do that again. We could do CASAViz to do with X forwarding. We could even run a script with CASAPy option C. We could run this inside our SBatch file, for instance, or we could even run CASA shell if we want to just shell into the container. And then similarly, we can do module avail Python, and we can look at, the Python versions that are available. So let me just quickly show that as my last thing. So I'm going to do, users J Collier training demos. So here's one that I prepared earlier. So I have this my script. It's basically just hello from the container and then sleep. And then I've also got a SLURM job script. So this is where our module load the specific Python version. So just quickly, if I do that and then I say which Python, it now knows, okay, this is the Python that I'm using. So if we go look at that, this is the syntax. So I could SBatch SLURM Python job script. And now if you see, if you look at my user, I'm now in the queue. I could choose to cancel that if I wanted, cancel and then the job ID. I'm not going to do that right now. And then you can see account is reporting this as running. You may even like account option X, which I'll show in the advanced. That does a single line per job. And then, so I'm going to say, yeah, what I wanted to highlight from SQ is it shows you the node count, if that's of interest to you. And then account shows the CPU count. So I could do my user again. Okay, it's now finished, and account will show, okay, that job's now completed. And then if we just quickly look at the output, there's nothing in standard error. And then in standard out, you can see it's got those things that I echoed, that I printed. Okay, so that's what I wanted to demonstrate. Just make sure I didn't miss anything there. Cool, yeah, that's everything. So let me just finish up on this last slide, which is the best practices. So just to reiterate things that Jeremy and I have said and a few other things. So yeah, the login node is where we're to run our SLURM commands like SBatch, SRun, SQ, and so on. It's not where we're to run our software and our heavy processing or even copying, as we'll talk about in the next training. If we want to do copying, we're to use the transfer.ilifu node, which we'll show how to do in the next training. But if you're ready to run your workflow, first identify the available resources with sinfo. It's generally best to not hog the cluster, but reduce your allocation if possible, although obviously some large projects will have reason to use a substantial portion of the cluster for a period. And then if you want an increased likelihood of your jobs running immediately, use less memory, use less wall time, use fewer CPUs. And if you can afford to do so, your job will be scheduled more quickly. We encourage the use of SBatch over SRun and things like Screen, if you know how to do that, or tmux, as those are volatile. And if, for instance, we need to restart the login node, those would be lost. As Jeremy talked about, clean up files that aren't needed. If you have old raw data or temporary products or scratch data, it very much helps us and all the projects we try to support if you go and clean that up. And then please don't place large files in your home directory, since this can negatively impact yourself and all users. And then generally, please use Singularity. We don't generally encourage installing software. There may be, for instance, Python virtual environments that you want to install, and we'll talk about how to do that in the next training. But in general, we will build your software for you in the Singularity containers. So please get in touch if you'd like to do so. Cool, so that's everything from me. Apologies that it's getting late, but we do have a little bit of time for questions now. So please either type in the chat or raise your hand or unmute and ask your question.
Thanks very much, Jordan. So we've got one question originally from Stabila, and that was, in terms of the timeout for Jupyter. So if timeout for the Jupyter server, if you don't stop it. So as I mentioned, we prefer obviously for users to close down the server when finished processing. However, there is a timeout functionality. So the we have a culling application that if a Jupyter session has been idle for 18 hours, then that session is closed. And then there's a maximum time limit for Jupyter sessions, so that's 5 days. So one Jupyter session can't extend longer than 5 days. And this is mainly just because it's a development space, not necessarily used for running long-term jobs. That would be better to submit to the queue via SBatch. So yes, there is a automatic timeout on the Jupyter sessions. And then O'Layton has asked the maximum wall time for interactive and batch requests. So for maximum wall time on the cluster for all the queues, I mean, I guess except for Jupyter, so that's set to 14 days, 2 weeks for the maximum wall time. Obviously, for an interactive job, it would be not ideal to request 14 days just because of the nature of it being interactive. If you want to doing command line interfacing with software, that sort of thing, generally you would only want to do that during development. So using SRun or interactive sessions is preferable to have a shorter wall time. In addition, if you have a shorter wall time, you'll probably also manage to acquire resources sooner. If you request large wall time, it tends to be delayed because it's waiting for resources to be freed up. SLURM has a backfill system where even though other jobs are long jobs are waiting for resources, if your job is very short, it will place your job as priority before other jobs that are still waiting for resources. So there is some benefit to providing a small wall time. Another point is actually accurate wall time. So the scheduler functions best when users specify an accurate wall time. If you know that your job is only going to run for 2 days, it's better not to specify 7 days, rather specify, obviously with the leeway, provide 2.5 days, for example, in case it might overrun. But a more accurate wall time makes the schedule itself more efficient and will allow your jobs to be submitted or allocated the resources faster. And then for defaults, so Oleg, your next question was defaults if you don't specify them in your script. The defaults, they are listed in our user documentation for reference, but the default is one CPU on one node with 7 gigs of RAM, and it's a default of a 3-hour wall time. So that's what you would be given if you just use the srun -pty command, or pty bash. So you would be automatically given 3 hours and those resources. Perfect. Does anybody else have any questions or for us? Obviously, you're welcome to contact us through support@ilifu.ac.za at any time. If you have any questions about the cluster. If you're looking for information, we can point you to the right resources. So please don't hesitate to contact us. So in terms of how the scheduler works, Leighton, your question is, I suppose the scheduler distributes jobs across all available nodes before allocating 2 jobs to 1. Actually, the scheduler works in a rolling state. So it uses, if it can assign jobs to, or 2 jobs to the same node. So if one job is using, say, 16 CPUs and another job is using 8 CPUs, those will tend to fall on the same node first. This is to allow for the chance of a larger number, for a job with a large number footprint of resources to also be allocated at the same time. If the scheduler had to assign like an 8 CPU job to a node and then a 16 CPU job to another node, it would prevent larger jobs from being given resources in a timely fashion. So no, it actually fills up the resources in a Tetris type of way, using nodes as the same nodes as much as possible.
Just to add to that, that doesn't mean that you will have the jobs interfere with each other. We have limits set in place so that the jobs don't go over their memory or CPU allocation. So if you're sharing a job with another user, they can't kind of invade your resource allocation. Yeah, they'll be limited to what they've requested. So it should be totally fine to have your jobs shared on nodes.
Jordan, you asked if, I guess, so, Leighton, in terms of your question about the maximum wall time, if you do have a job that requires longer than 2 weeks, you can email support and ask us to extend a job. So if you see that your job may not be complete by the wall time that's been specified, you're welcome to email support and we can extend a job's lifetime. The only other recommendation regards to that is that longer jobs tend to have more chance of failing. So if it's possible to separate a pipeline or workflow into multiple jobs and even dependencies, which Jordan will talk about in the advanced training workshop. So having multiple shorter jobs is much lower risk than submitting long-term jobs. But obviously this may depend on the software and the data structure that you're using. So obviously there are other factors involved.
Yeah, so in general, I guess it's better to request smaller wall times, but you obviously want to make sure that you allow for headroom, in case your job takes longer than expected. But I guess rather than go very high, we'd suggest that you just leave a little headroom. And if it's coming to the end of the process and you're worried about it being killed before the end, then you could email us and ask it to be extended with enough notice for us to attend to that. So we would encourage that over, grossly overestimating your wall time, because then SLURM won't work as well as expected. And, where it could have allocated resources earlier, then it wouldn't do so if everyone's overestimating resources and wall times. But it is tricky to do. So yeah, we can help you with that if you want.
So if there are no more questions, I just want to point out that our next training workshop will be held on the 13th of April. It's also a Tuesday at 10 a.m. We'll be covering additional kind of introductory topics, such as the transfer nodes and different transfer services, and more advanced topics, such as more advanced topics about building containers and advanced parallelism with jobs on the SLURM cluster, which Jordan will go through, and a number of other topics. we'll send out an email with those topics and a reminder about that workshop closer to the time. But thank you, everyone, for joining us today. I appreciate you coming to the workshop.
Yeah, thanks, everyone. And hopefully see you in 2 weeks.
Cheers, Dane. Bye, everyone. Thank you.
Thanks. Bye.